In this tutorial, we're going to be examining the sensible or conductive component of the heat flux that's part of the Earth's energy balance. The four heat components are shortwave, which we examined in another tutorial. The backscatter or long wave we examined in a separate tutorial. And now we're going to be speaking about the conductive or sensible heat component. It's a fairly complex mechanism by which heat is transferred in the conductive sense between the ocean and the overlying atmosphere. So we're going to start by looking at a simple example before we get into trying to understand how that works. Consider a classroom separated from the outside air by a wall. Here's the inside with temperature Ti. Here's the outside with temperature T out. Now, if you think just intuitively, if Ti is greater than T out, and these bars are the wall, and this wall can be filled with some medium, it could be glass or aluminum or fiberglass or vacuum or foam, whatever it is, this is the wall. And if Ti is greater than T out, intuitively we would say that the heat moves outside, moves from the inside to the outside. If the inside temperature is less than the outside, let's say it's summertime, then the heat is going to move into the classroom. So the difference in temperatures will determine the direction of travel, and if the inside and outside temperatures are equal, then we would have no heat travel. At some point we get across to zero here. And that the greater, if we have greater delta T, as delta T goes up, our heat flux, which I'm going to denote Q, will also go up. A greater temperature difference will lead to a larger heat flux. No temperature difference will lead to no heat flux. So what else influences our heat flux in this simple problem? Well, one could be the properties of the wall. As I mentioned before, we can fill this wall with different materials. It could be metal or foam, and let's consider those two cases, such that we can assign a property to this material, which we're going to call K, which is known as the thermal conductivity of that material. And the units of that are going to be watts per meter degrees Kelvin. The higher the thermal conductivity, the greater the heat transfer. Metal has a high thermal conductivity. The lower the thermal conductivity, the lower the heat transfer. Things built for insulation like fiberglass are specifically designed to have low conductivity. Conductivity you can feel if you put your hand down on a piece of metal or on a piece of wood, for example, where they have reached room temperature and you are a temperature higher than room temperature. The metal feels colder, but it's not actually colder. It just feels colder because it's a good conductor and it's pulling heat out of your hand faster than the wood. So the nature of the material determines how well it conducts heat. Metals conduct heat very well. Foam conducts heat very poorly, which is good if you want to use it for insulation. Now, what else might determine the amount of heat flux? What if I doubled the thickness of the wall? I filled it with foam and I doubled the thickness of the wall. What if I multiplied it by 1,000,000? Well, that should also increase the insulation ability or resistance to heat flux properties of the wall. So I have this distance, which I will call delta X. So I have a thickness of the wall, I'll call delta X. I have properties of that wall, which I will summarize as K, the thermal conductivity, and I have the temperature difference across the wall. I can put all those together and come up with a law. Let me just refresh the page here. I have the wall. It is filled with material K. It is a thickness delta X. The inside classroom temperature is Ti. The outside exterior temperature is T naught. And this is my direction x. My heat transfer through the wall can be written as Q equals minus K delta T over delta X. So it's positively correlated with the conductivity, the thermal conductivity. A higher conductivity means faster heat transfer, everything else the same. A larger temperature gradient means higher heat transfer. A larger thickness of the wall means lower heat transfer. And as the wall thickness goes to infinity, our heat transfer goes to 0. The minus sign works correctly because if, and I'm going to write this in our sense here, we have minus K times T outside minus T in. That's a change in temperature as we increase X going from left to right, divided by the change in distance, which is delta X. So if the outside temperature is greater than the inside temperature, then we have Q is negative, and that's correct. The heat is moving against the X direction, counter to the X direction. If the inside temperature is warmer than the outside direction, then we have a positive Q, and the heat is moving from left to right in the sense of positive X. So that is where that minus sign comes from. So this is known as a Fickian heat transfer. You can see it depends linearly on the conductivity, linearly on the temperature gradient, and also depends on the thickness of the wall. Let's just run some numbers. I'll try to make some up here. Let's say we made the wall using those little, I can't draw very well, but those little concrete things you can buy. I forget what these call, cinder blocks, which are about 20 centimeter wide. They have a K of about 1 watt per meter Kelvin. And let's say our temperature difference is, I don't know, an inside temperature might be 70 degrees in the winter, so we say 20 Kelvin. So delta T is going to be T outside, which will be 0. Say it's wintertime, it's basically freezing outside. 0 Kelvin minus inside temperature of Celsius, 20 Celsius. So delta T could be written in Kelvin or Celsius. It doesn't matter because delta Kelvin and delta Celsius are exactly the same. The scales are just shifted relative to each other. So I'm going to put T naught equals 0 and T in equals 20. I'm just making up these numbers. These might be a typical wintertime New England scenario. And the thickness of that block is 20 centimeters or 0.2 meters, and K happens to be 1. So if we do Q equals minus K delta T over delta X, this is going to be equal to minus 1 times negative 20 divided by 0.2. This is equal to 100 watts per meter squared. Now be a little bit cautious because Q is sometimes an energy and not a power. Q is sometimes just watts, and sometimes it is watts per meter squared. Here it is watts per meter squared in the sense that for every meter squared of wall I have 100 watts moving through that meter squared, given the walls that I made, these cinder block walls, and the temperature difference that I made up. So then if we consider our classroom wall is about 3 meters high and, 10 meters long, so you have 30 meters squared of wall. Now if we multiply Q times the area of that wall, I get 3,000 watts per meter squared, or about it's not per meter squared, it's 3,000 watts now. So that's an actual power, which is 3 kilowatts. Now, over the course of a day, 24 hours, that would be 3 times 24, which is 72 kilowatt hours. And at 10 cents per kilowatt hour, that comes out to about $7 worth of electricity, assuming we have 100% efficient conversion from electricity to heat, which we do not. Seems like a lot. I hope my math is correct. That seems absurdly high. Now, if we take the case where we actually use an insulator rather than brick, the only thing that changes, let's say we keep the same thickness of the wall, we aren't really not in control of the interior and exterior temperatures. We like it to be 20 Celsius in the room. The outside is up to Mother Nature. And so that leaves us, let's just change the material of the wall, K. We'll make the wall out of foam or insulation. Insulation typically has Ks that are much smaller, I think around 0.02 or 0.03. So if we use K equals 0.02, so this is with my K equal 1 cement. If we use K equals 0.025, we'll call it, nice round number, we get that the heat loss cost, assuming again 100% electrical to thermal energy transfer, is now about 17 cents. It's 17 cents. So you can see the power of insulation and why you need insulation, particularly in the Northeast area. We've gone from having spending dollars a day to heat this, to keep the room heated with this just one exterior wall, to cents per day. Now, when you go to buy insulation materials and housing, they're often listed using this R value, which is related to K. R is essentially the resistance, heat resistance or thermal resistance. And I think what they do is basically say for a given temperature gradient, what is the heat flux through this material? So includes, wrapped up in that is the thickness of the material. And that you'll see R values listed for insulation. It's kind of like an inverse conductivity. It's a resistance such that the larger your R value, the better. Whereas conductivity, the larger the K, the worse, if your goal is to try to reduce heat losses. So that's a basic idea of heat transfer driven by a temperature gradient, conducted by the material with a material property K, and the material having a thickness delta X. So again, the law looks like this. Let me plug some numbers in, and you may want to double check those. So what happens in the atmosphere? Obviously, it's not a hard material. We're dealing with a fluid system. It is far more complex, but there are some similar ideas, which is important. When do we have conductive or sensible heat flux? And we're talking about fluxes between the ocean and the atmosphere up here of the conductive type. When does heat move between them? Well, when there's a temperature difference, no different than the previous example. If the air temperature is high and the ocean temperature is cold, heat goes from the atmosphere into the ocean, just like when heat left our classroom during the winter. And the opposite happens when the ocean is warmer than the air. We're getting to that time of year now, fall. Ocean is warmer than the air. Now the ocean loses heat to the atmosphere. We have the same analogy. The direction depends on which is warmer. The amount of heat transferred will depend on the temperature difference, such that if you have no temperature difference, you will have zero heat transfer. So you have direction and temperature difference driving the magnitude of the heat. What we don't have here is a solid object through which we're conducting the heat. In between these two is air. Air is conducting the heat between these two. And that air is moving. It's moving around, swirling around. So it's a more complex situation. But we can make some analogies. The conductor, the properties of that conductor, it's always air. That air might be humid and that air might be moving around, but it's always air. What is different is how, in terms of the conductivity, the effective conductivity, K, from our previous example, the analogy here is how much that air is swirling around. If there is no wind, the air is essentially still or moving very slightly. In this case, the conductivity is very low. You have air-sea temperature difference, but how much heat is moving depends on the air being able to move it up and away from that ocean. But if it's still, it's unable really to transport the heat up and away from the ocean. If you put a strong wind in, which leads in general to a turbulent boundary layer, and if you were to visualize that, you'd have lots of little eddies swirling around, and what they do is they grab heat from the surface and they mix it up with the atmosphere where it's cold, and they take the cold air from the atmosphere and they swirl it down to the surface, thus leading to a much more rapid exchange of heat for a given temperature gradient. The only difference between these two cases, not the temperature difference, it is whether it is windy or not. So this is effectively a large K. It's not really K anymore, but it's a large K. And this is like a small K. What people do to quantify this, and it's complex, it depends on turbulence. That turbulence depends on the stratification in the air and the roughness of the sea, if there are waves, and how much wind there is and humidity. Very complex relation. But there are people that boil those complex relations, or try to, down into some kind of effective conductivity, which we call here the eddy diffusivity. It depends on these turbulent eddies. And this is like a measure of K from our classroom heat flux example. And that's what people do. Come up with what is this, the value of that, given the wind conditions, the wave state, if it's available, the humidity, if that's available, and the air-sea temperature differences and other things. Come out with a value for that, which allows us to quantify this heat flux. The mechanism is quite similar to our classroom, except it's being conducted through a fluid that's moving around, and the nature of how it's moving around depends on all those conditions. So in the end, the key thing is air-sea temperature difference, just like the classroom example. Larger air-sea temperature difference, greater heat flux. The direction of that, of course, depends on which is warmer, so it's important to think about. And then we have an effective conductivity that is most dependent on wind speed, also somewhat dependent on the sea state, but most dependent on wind speed. Greater wind speed, greater conductivity, greater transfer of heat from the water. What does it look like spatially varying? Well, there's big differences between seasons. Let's focus on the northern hemisphere. Let's focus on the North Atlantic, actually. This is over here. It's between these two seasons. In the summertime, the air is a bit warmer than the water, but by the time we get to the end of summer in our area, the water's getting approaching 70. That's not much different than the air temperature. So you have small negative, in this sense here, heat flux, meaning that the heat is moving into the ocean. And this convention here, if the sensible or conductive heat flux is negative, it's moving into the ocean. Small negative heat flux in our region, the Northwest Atlantic. Once fall comes and winter comes, then we have the overlying air being much colder than the ocean temperature. In that case, you can have fairly large sensible heat flux in our region here. But this is particularly true in sort of late fall, when you begin to get cold, dry winds from Canada that are much colder than our ocean, which is still in the process of cooling off from summer, delayed from the atmosphere cooling. So that's when you have strongest positive heat flux, meaning heat's getting sucked out of the ocean into the atmosphere. It is cooling the ocean, these cold winds. Compared to the other heat flux components on a global scale, this one is small. It is important regionally, particularly in regions, as you can see, that are on the eastern side of these continents. They're affected by the wind patterns, the seasonal wind patterns. In the rest of the ocean, it's kind of green, which is close to 0, 5-10 watts per meter squared. So you have areas with strong variability, seasonal, and much of the ocean, the sensible heat flux is quite small.